Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about symmetric and zero-sum games. My name is Rick, and my co-teacher who originally prepared these notes is Christoph. So this is going to be a pretty short lecture, I think. You'll appreciate that, I'm sure. We just really have two concepts to talk about. And of course, those are symmetric games, and maybe you can guess the next one, zero-sum, or also called constant sum games. Okay, let's talk first about symmetric games. This is a term that will come up again and again, so you should get comfortable with it and add it to your glossary. The basic idea behind a symmetric game is that you have two players, a row player and a column player, and they both play the same game. And what I mean by that is that their roles are interchangeable. In particular, the payoff matrix is the same after you swap roles. So let's look at an example to see how that works. Let's say we've got two players. Let's say we've got Ricky and Chrissy. Ricky, let's say, has two options. He can play U or D, and Chrissy can play L or R. Let's say the payoffs, very generally, are just variables for each of these players. For Ricky, we'll make them Roman letters. Let's say they're A, B, C, and D. And for Chrissy, let's say they're Greek letters. Let's say alpha, beta, gamma, and delta. You might notice I didn't put the beta next to the B and the gamma next to the C. I'll explain. Well, it will become a little bit clearer why I did that later. Okay, so we've got this payoff matrix, and now imagine we swap roles. So same players, we just want to swap who is the row player and who is the column player. We'll leave the colors the same. Ricky will be red, Chrissy will be blue. Let's see what happens. What will the payoff matrix look like under this switch? Well, we'll have Chrissy as the row player with options L and R, and we'll have Ricky as the column player with options U and D, and we just have to fill in the payoffs. So the payoffs are going to be exactly the same as each box in the original matrix, except we have to order them in the right way. So the top left box, so this box, is a combination of U and L. So that'll still be here. Now it's L and U. We always write the row players payoff first and the column players payoff second. So we'll put blue first this time. And the payoff will be alpha and A for Ricky. Now pretty clearly, if we look at the D and R, that becomes R and D. So that's here. So the bottom right stays in the bottom right. And the payoffs are delta and D. The only place things get a little bit weird is the off-diagonal elements. If we want to see what goes in this box, well, we have to see what combination of strategies that outcome represents. And it's L and D. So L and D in the original matrix, L and D, is this bottom left box. So we actually end up swapping the off-diagonal elements when we swap the roles in this game. So the top right will be beta and C. And likewise, the bottom left box has to be, the bottom left box here has to be the payoffs for the outcome with U and R. U and R is this box, the top right box. So again, we swap the roles, which means we swap the off diagonals. So the payoffs are gamma and B. effectively what we've done is we've taken that 2x2 matrix and we've flipped everything around the diagonal. Sometimes that's called transposing. And that's how we got from this original payoff matrix to our new payoff matrix. So in a symmetric game, we have reflection symmetry or mirror symmetry, which means that the payoff matrix is unchanged after the flip, which means that this payoff matrix must be the same as this payoff matrix. And all of the corresponding elements must be the same. That means the strategies need to be the same. So that means that L and U have to identify with each other, and R and D have to be identified with each other. They have to be the same thing. Or in other words, L is U and R, the strategy R, is the strategy D. And likewise, the payoffs also have to be unchanged after the flip. So that means that not only the boxes have to be the same, not just A and alpha have to be the same here as alpha and A, but the individual elements, the payoff to the row player, for example, here, has to be the same as the payoff to the row player here, which means that A is alpha, and likewise, B is beta, C is gamma, and D is delta. So a small point here, symmetric games must have square matrices. So for a general M by N game, we must have M is equal to N. In other words, we have the same number of rows as columns. Think about that. Convince yourself that it must be true. Figure out why that's true. So if we have that, then we can write our payoff matrix in a simplified way. The idea of the term a simplified payoff matrix, we'll run across that occasionally. We'll be using simplified payoff matrices a lot, and we'll use the term occasionally. So you should be aware of what it means when we say that. In this case, we can write our simplified payoff matrix as simply A, B, C, and D. And compare that with the original matrix. You'll see that it's the A, B, C, and D represent the payoffs to the row player. And because we know the roles can be swapped, we automatically know what the payoffs to the column player are if it's a symmetric matrix. Let's just write them down. If our simplified payoff matrix is a symmetric matrix, then the payoffs to the other player are just given by... First, let me write down the payoffs to the first player, the row player, and think about what the payoffs are for the column player. Maybe pause the video right now and see if you can work out what the payoffs must be. Okay, let's get to it then. If both players play U, then the row player gets A, which means the other player must also get A. If both players play D, again, we can see that the payoff to both players must be little d. What about the off diagonals? Let's say the row player plays U, so the row player plays U, the column player plays D. Then we see here that B is a payoff to the row player. What would the payoff be to the column player? We can figure that out by looking at the perspective of the column player and swapping roles. If they were the row player, the new row player, then they would be playing D, and the other player would have been playing U. So they get C. Now we go back to the original perspective of the original row player, and we see that in this case of U and D, the second player must get C. And by the same reasoning, in the bottom left box, the payoff to the column player is B. And if that was difficult for you to follow, it might make more sense if you just look at the payoff translation here, that A equals alpha, B equals beta, and so on, and apply those in this original payoff matrix, and you'll get the same result. So the point here is that you can write a simplified payoff matrix with just 4 values in the boxes, and it can represent a full payoff matrix if we know that we're talking about a symmetric game, because we can infer the payoffs for the other player, and we don't need to write them down. We'll be doing that a lot in this course, so you should get used to the idea. Moving on, let's talk about zero-sum games, which are also called constant sum games. So in this case, the sum of all the players' payoffs is the same for all outcomes. So if you add up the payoffs within any one box, you'll see that the sum is the same across all the boxes, across all the outcomes. In a zero-sum game, that sum is 0. So you add up the payoffs for both or all the players, and they will add up to 0 in every outcome, in every box in a payoff matrix. And that means that a higher payoff for one player comes at a cost to the other players, or other player. So let's look at our general payoff matrix again. Here it is. In this case, what we're saying is that the sum of these values has to be equal to 0 in a zero-sum game, and the sum of these has to be 0, 0, and 0. So A plus alpha is 0, and so are the others. And that's the definition of a zero-sum game. The term zero-sum or constant sum will come up occasionally in the course, so you should remember what those are. Again, we can write a simplified payoff matrix. And it looks very similar to a simplified matrix for the symmetric game, but it's different in some very important ways. So let's say the column player plays L and R still, the row player plays U and D. The payoffs can be written as A, B, C, and D. And again, these are the entries for the row player. So they tell you the payoff that the row player will get, that is playing U or D. And if this is a zero-sum game, then we can infer what the payoffs for the column player are. And we can build out the full payoff matrix. So again, it's A for the row player, B for the row player, C for the row player, and D. If it's a zero-sum game, that means that these 2 elements have to add up to 0. So obviously the other one has to be minus A. And here it has to be minus B, minus C, and minus D. So again, if we know that we have a zero-sum game and we have a simplified payoff matrix, then we can get the full matrix and we can figure out what the payoffs are for both players. Let's briefly talk about constant sum games. They're very much the same as zero-sum games, the only difference being that the payoffs don't have to add up to 0, but they have to add up to the same constant for all the boxes. So A plus alpha still has to be the same as B plus beta and the rest, and that has to equal, let's call it K, some constant. If K is 0, we're back to a zero-sum game. So at first glance, you might think this is a slightly different beast than a zero-sum game. For a reason we haven't really touched on yet, they're actually the same. So I'll just briefly mention it, and we'll get into it more in a later lecture. The essence of the argument is that rational choice how to choose between the strategies only depends on differences between the payoffs for a single player. It's not the absolute numbers that go in these boxes that matter, but rather the differences, the difference between A, B, C, and D. Those are the things that matter when somebody is trying to choose between their available strategies. We can talk about why that is a little bit more later on. But given that, we can subtract off a constant from every outcome without changing the essence of the game. And that means that every constant sum game is essentially a zero-sum game. Let's look at a particular example. Let's say we have 2 players. The row player plays U and D. The column player plays L or R. And let's say the payoffs are like this. 20, 80. Let's say again 20, 80. How about 50, 50, and 80, 20. You'll notice that this is a constant sum game. If we add up the top left box payoffs, A plus alpha, those are 20 and 80 respectively, and they add up to 100. And if you add up all the other boxes, B plus beta is 20 plus 80, C plus gamma is 50 plus 50, and D plus delta is 80 plus 20. They are also all 100. And since all the boxes add up to 100, this is a constant sum game. So because of what we just said, that we can subtract off a constant from every outcome without changing the game, let's subtract 100 from the row player. And we have to do the same in every outcome. So let's say we have a new A prime after doing that, and that's equal to A minus 100. And we have a new B prime, and so on. Then our new payoff matrix will be, the first element will be 20 minus 80 now, so it's 20 minus 100, which is minus 80. And the second payoff in that box is still what it was before, 80. Moving to the right, we started with a 20, we subtract off 100, and we have again minus 80 and 80. Moving to the bottom left, we now have minus 50 and 50, and the bottom right is minus 20 and 20. And you can see for yourself, this is an example of a zero-sum game, because our new payoffs, A prime plus alpha, is the same as B prime plus beta, and so on. And they are all equal to 0. So we can translate any constant sum game into a zero-sum game just by subtracting the same number from all the payoffs to one of the players or the other player. In fact, alternatively, we could have subtracted 100 from the column player, or we could have done something even funkier. We could subtract any amount X from the row player and some other amount Y from the column player, just so long as X plus Y add up to 100. So in the end, we're subtracting 100 from the sum of the payoffs in every box. So I hope you see now that constant sum games are effectively zero-sum games. That also means that solution concepts always give the same results. Let's say predict the same outcomes for constant sum games, and their equivalent zero-sum games. So we've looked at two different ways of writing or interpreting a simplified payoff matrix. It could be a symmetric game or a zero-sum game. For the purposes of this course, let's establish a convention. Unless it's otherwise stated somewhere, when you see simplified matrices, they will indicate symmetric games. Okay? So if you are looking at a simplified matrix, you can safely assume that it's a symmetric game unless it says it somewhere explicitly that it's a zero-sum or constant sum. Okay, let's just review what we did today. We talked about symmetric games and simplified payoff matrices. We also covered zero-sum games or equivalently constant sum games. And we established a convention. Simplified games or simplified payoff matrices imply symmetric games, unless we explicitly say otherwise. Well, that's all I've got for this lecture. Thanks for watching.